Hello, our project name is Diesel Wings. My name is Omar Mohammed, and I am a current junior at STEM High School for Boys.
And I'm Mohammed Shehata, a junior at STEM High School, and this is our project, Diesel Wings. The globe faced a lot of grand changes throughout the past few decades, which have been growing rapidly and haven't been solved efficiently yet. Some of those grand changes are rapid population growth, pollution, a lacking industrial base, but most importantly, the lack of a stable power supply. The purpose of our study is to provide a new stable power supply without contributing to global warming. As shown in this graph, the data shows that the increase in energy consumption around the world along the years, which is very critical. This project wasn't the first to attempt to provide a new stable power supply without causing pollution, as it was done before using vegetable oils to produce biodiesel. However, that project wasn't effective as the vegetable oils used were high cost efficient for the transportation process. Furthermore, the biodiesel produced had high ash content, high moisture content, and lost a lot of energy during the process too. Thus, after thorough research and studying of power solutions, a biodiesel generator that depends on chicken feathers was designed. The prototype chosen fulfilled the design requirements, which were efficiency and cost. We created a prototype which consists of multiple stages: the pre-treatment stage, the transestification process, and the pyrolysis process. Several materials were used during the building of this prototype, as now illustrated with Omar.
Right. We used methanol, sodium hydroxide, isopropyl alcohol, phenolphthalein, templates, a mixer, a plastic container, chicken feathers, and plastic pipes. We followed some procedures to construct our prototype. At first, we extracted the chicken fats from the chicken feathers using the succulent device. Then we filtered it using a tea infuser, as shown in this figure. After that, a sample of 1 milliliter of oil and was taken, and 10 milliliter of isopropyl alcohol and 10 drops of phenolphthalein was added to it for titration, as shown in figure 2. Then the number of millimeters taken from the titrating solution were added to 3.5 to determine the amount of needed catalyst to start the reaction. In the transfer process, 6.5 grams of sodium hydroxide were added to 200 milliliters of methanol and stirred using a magnetic stirrer. After that, the solution of sodium methoxide was added to the oil and stirred for 1 hour under 60 Celsius degree. After that, the two products were produced, which were biodiesel and the glycerine. They were easily separated by downward displacement, as the density of glycerine is much greater than the density of biodiesel, which make it sink at the bottom of the container, as shown in figure 4. Finally, the produced biodiesel was washed using distilled water to remove excess alcohol, catalyst, and soap. For the pyrolysis reactor, templates were used to make the container, and we made a hole in the middle of it to attach the plastic pipe and transfer the heat energy from the pyrolysis reactor to the biodiesel. This method allowed us to achieve our requirements and generate successful results that will be illustrated with Muhammad.
Right. After testing the prototype, negative and positive results were deducted. One of the negative results was the emulsion produced during the washing of the biodiesel. This was due to the wrong estimation of the solid catalyst NaOH purity to be around 85%. However, it was discovered to be higher. It was detected that less NaOH was required for mixing with the cooking oil to correct the process. On the other hand, some of the results deducted were positive. Firstly, after testing the biodiesel properties at Ministry Petroleum Research Center, and after careful consideration of the results of the test plan, the produced biodiesel was found to have achieved ASTM standards. The minimum value of flash point in ASTM standard is 93 Celsius, which limits the presence of residual alcohol in the biodiesel. The viscosity was also in the accepted range of kinematic viscosity at 40 Celsius for B100 diesel, from 1.9 cent to sink to 6.0 cent sink. Furthermore, the calorific value of the produced biodiesel, 42.2 megajoule per kilogram, was close to the calorific value of petrodiesel, which stands at around 45.5 megajoule per kilogram. Several processes were used to achieve these results, which will now be discussed with Omar.
Substrate extractor has three main sections: a percolator, which circulates the solvent; a thimble which retains the solid to be loved, and a siphon mechanism which periodically empties the thimble. The mechanism of the device mainly depends on heating the alcohol in the percolator and then condensing it above the thimble, which contains the solids that we would like to extract the fats out of it. Then, after the thimble is filled, the siphon empties it, and the cycle repeats itself all over again until the desired compound is extracted. Biodiesel processing usually depends on three reactants, which are alcohol and NOH and oil to produce biodiesel and glycerine. Before starting the reaction, we must neutralize the free fatty acid as it will react with alkali catalysts to form a soup that may prevent the reaction from occurring. The method used in the pre-treatment phase is base titration. In this method, an excess amount of alkali catalyst is added to the oil to allow a portion of NOH to neutralize the free fatty acids by forming soup, which still have an amount of sodium hydroxide to act as a catalyst for transcertification reaction. This soap will be eliminated by washing as discussed earlier in the methods, which will be used, in which distilled water will be used to remove the catalyst, excess catalyst, and soap and excess alcohol. The amount of excess catalyst used is determined by calculating its acid value of the oil, as discussed in the method also. The reaction of triglycerides in fat or oil with an alcohol to produce esters and glycerol is known as the transcertification reaction. Transcertification is made up of a series of reversible reactions. The triglyceride is converted into diglyceride, monoglyceride, and glycerol at the end of the reaction. A catalyst is typically used to increase the rate and the yield. Excess alcohol moves the equilibrium to the product side because the reaction is reversible. Because of its inexpensive cost and physical and chemical properties, methanol was used as an alcohol, and the basic catalyst, which was sodium hydroxide, was used as a catalyst. The needed methanol triglyceride molar ratio is 3:1, and according to stoichiometry, this is not enough to complete the reaction in practice. A higher molar ratio is necessary to accelerate the reaction completion. The reaction yield rises as molar ratio increases, as shown in Figure 6. The amount of the sodium catalyst NOH used in the transcertification process is one of the most important factors, because the addition of an excessive amount of catalyst results in the formation of an emulsion that increases the viscosity. And according to Figure 7, 0.5% NOH achieves the maximum conversion efficiency. In the pyrolysis reactor of our prototype, chicken feathers are burned and used as a source of heat. After the process ends, these carbonized chicken feathers can absorb as much or perhaps more hydrogen than carbon nanotubes or metal hydrides in cars. Also, they are better than those other systems in hydrogen storage and are cheaper in money. For further development of our prototype, we would like to add some recommendations and applications that will be illustrated with Mohammed.
Firstly, we will watch now a video of the test plan. First, we put oil. Then we put methanol, as shown now in the video. We also put sodium hydroxide.
This is sodium hydroxide of no molarity. Then we move to the process that happens in the pyrolysis reactor, where we burn chicken feathers to provide the source of heat for transcertification process, and also to allow the chicken feathers to absorb hydrogen, such as the carbon nanotubes.
Now we're going to state some conditions and applications for the real-life project. Firstly, we recommend using an ultrasonic mixer instead of the kitchen mixer we used, as it's much more efficient. It converts all the methanol into biodiesel without increasing the molar ratio of the alcohol, hence increasing the yield of the biodiesel. In addition to that, the ultrasonic mixer uses a smaller portion of energy than the ordinary mixer consumes, as shown in the graph.
Finally, if you have any question, please feel free to contact us via email. Thanks for your attention.
Yes, thanks for your attention.